Hi, I'm Grant Connette, and I'm a research ecologist at the Smithsonian Conservation Biology Institute. It's a pleasure to be able to share a project update from our team of collaborators at the Smithsonian and the Worldwide Fund for Nature. This project is centered around a planned highway development in the country of Myanmar. The Yaji-Kalewa Road is a project financed by the Indian government as part of the flagship India-Myanmar-Thailand Trilateral Highway Project. There's currently an unimproved dirt road along most of the planned alignment, and this section of road is intended for upgrade to allow for an increased flow of people, goods, and services, eventually connecting Thailand to India via Myanmar. A section of the Yaji-Kalewa Road is currently planned to pass through the Alaungdaw Kathapa National Park. Alaungdaw Kathapa is Myanmar's oldest national park, covering an area almost twice the size of Singapore, and it's an important habitat for a whole suite of threatened and endangered species like elephant, leopard, gaur, and Asiatic black bear. Recognizing, however, that biodiversity is just one consideration, and frequently a minor one for project planners, we challenged ourselves to assess alternative routing or alignment options for this highway project, using an analytical approach that was able to combine multiple objectives, minimizing construction costs, bringing economic benefits to the surrounding region, and avoiding environmental impacts to sensitive areas. In a nutshell, we have a situation where we know the intended start and end points of a section of road, and we want to avoid multiple types of costs to identify a win-win solution. In this simple graphic, the green area might represent a protected area, while the blue area might be an area of higher construction cost. In our study, we specifically attempt to minimize the total paving cost, the projected cost of earth moving, which depends a lot on the terrain being traversed, and the differing cost of land acquisition or clearing for agricultural versus forest land. We also want a safe road that meets design criteria for road gradient or steepness, and we want the option for the road alignment to prioritize connecting population centers and agricultural areas. In theory, this would be expected to bring local economic benefits by reducing travel time for goods and services. Last but not least, we also want the option to explore potential alignments that completely avoid environmentally sensitive areas. If we can express each of these different individual design criteria as a cost or penalty, then we can add those costs together and calculate a single cost, total cost, for any proposed alignment. For our project, we implemented a genetic algorithm approach to alignment optimization in Google Earth Engine, which is a web-based spatial analysis platform. The idea behind this approach is that we create a large number of random proposal routes from point A to point B. We calculate the total cost summed across all our different design criteria. Then we iteratively repeat this process of keeping only a subset of the lowest cost routes, discarding all the rest, and then generating an equal number of new routes that involve random modifications to the existing alignment proposals. This is a bit like the infinite monkey theorem, that monkeys typing randomly on typewriters for an infinite amount of time can eventually produce a Shakespeare sonnet. That said, one of several ways that Google Earth Engine is an improvement over your own personal typing monkey factory is that the ability to implement a genetic algorithm approach means you're constantly selecting only the best routes and randomly modifying those rather than relying completely on random chance. Here's a visual showing the evolution of a route from iteration to iteration if our only criteria is paving cost. Eventually, our best route should be more or less a straight path between our start and our endpoints. Here's a more complex scenario where we impose a penalty to any section of road that crosses the Alaungdaw Kathapa National Park, which is not indicated but covers the elevated plateau in the center of this map. We also now consider land cover dependent costs of land acquisition and clearing, as well as earth moving costs, which depend on the terrain that would have to be traversed. Developing cost estimates for different road alignments requires not only the analytical tools, but a lot of country, region, or site-specific information and know-how on road design and cost estimation. Before the 2020 military coup and the overthrow of Myanmar's partly democratic government, WWF was engaged with both the Ministry of Construction and the Ministry of Natural Resources and Environmental Conservation concerning this planned road project. At the time, we learned that the Ministry of Construction primarily identified potential road alignments through field surveys and the process of manually consulting available satellite imagery. We were even told that this process enabled government planners to find alignments that preferentially crossed forest land that the government managed, such as protected areas and forest reserves. You don't need to focus on the details here, but through our contacts at the Ministry of Construction, we were able to obtain a number of key design criteria and cost estimates, such as typical highway width, maximum gradient allowed, paving cost per unit area, earth moving cost per unit volume, and the costs of acquiring and clearing land. Finally, we followed a published approach to disaggregate national level gross domestic product data by assuming that agricultural GDP is distributed across cropland and that GDP from the service and industry sectors are distributed according to the spatial distribution of nighttime light data as observed by satellite. The map on the left shows the predicted distribution of economic activity in the upper part of Myanmar, and the map on the right shows a zoomed-in view of the project area we assessed for the section of road connecting the towns of Kalewa and Monywa. We ultimately used this dataset to give extra credit to routes that pass through areas of higher projected economic activity. With our analytical approach and cost estimates worked out, we turned to a scenario modeling framework to identify optimized alignments under each of 4 scenarios. These scenarios involve different sets of environmental and economic objectives, either avoiding or not avoiding protected areas, and prioritizing or not prioritizing routes that connect areas of higher economic activity. Given that this highway project is being planned as an upgrade of an existing road, we assumed that a large realignment would be cost prohibitive and decided to explore a relatively small realignment of a 25.6 kilometer stretch of existing road that currently bisects the northeast corner of the national park. The optimized alignments under each scenario are shown, from scenario 1 on the left to scenario 4 on the right. Alternative routes identified for this road section range from 26.8 kilometers under scenario 1 to 59.6 kilometers in scenario 2. Routes that avoided the park or prioritized economic activity entailed additional travel times of 14 to 17 minutes if we assumed a speed limit of 60 kilometers per hour outside the park and followed the Indian standard for speed limits in protected areas of 25 kilometers per hour. Construction costs, that's the sum of paving, earth moving, and land acquisition and clearing costs here, were projected to vary from being roughly equal to the original route in scenario 1 to being double or more in scenarios 2, 3, and 4. While this may seem like a significant added cost, the proposed realignment would involve a relatively small portion of the entire 350 kilometer stretch of road planned for upgrade. As an example, proposed realignments that avoided the park completely would entail a modest green premium of between 8.5% and 9.5% on the overall paving cost for the road. Another benefit of the realignments that avoid the park is that they all entail significantly less total elevation gain. The figure on the left shows the elevation of the proposed road if the park is not avoided and economic benefits are not prioritized. This is very close to the original route proposal. The figure on the right shows the altitude profile of the route that avoids the park and prioritizes connecting areas of higher economic activity. The routes identified under the 4 scenarios all crossed a forested ridgeline inside or northeast of the national park, but both routes that avoided the park crossed the ridge at a lower point, which may be better for driver safety and fuel efficiency. For those advocating for avoiding environmental impacts of infrastructure, this approach allows for a reasoned discussion of costs and benefits, such as the projected increase in construction cost under different scenarios. And rather than simply identifying problems with proposed alignments, we can also help identify solutions. This approach is all coded in JavaScript in Google Earth Engine, so it can be adapted and improved on without involving paid software. Few caveats to this approach are, first, that certain costs are not included, like the added costs associated with bridges, culverts, and tunnels that may be considered for different road alignments. Related to that point, it's important to remember that these cost estimates are approximate and more of a starting point for discussion when different alignments are being considered, and that field surveys and calibration, particularly of earth-moving costs, are likely required. Thanks everyone for your time and attention. Your questions and input are welcome, so feel free to ask in this session or reach out by email. Thank you.
So thank you. I think that he is not with us today. So if you have any questions, please do not hesitate to send him an email or to use the app of the conference